So we have about 30 minutes, and are you ready?
Yes, I've been looking forward to this interview all week, actually.
Great. Okay. So at the beginning, how about you tell me a project that you have to learn new skills or new technology? So what was your experience?
That's a great question. So the first thing that came to my mind was a project that I worked on actually in Galvanize. It was my capstone 2 project, if I recall correctly. But it was basically I set out to build an analytics platform for the CEO of a company, and talk about doing something I'd never done before. I'd never built out a dashboard. I had never connected. I'd connected data sources, through analytics pipelines before, but I'd never done it through Salesforce through using their API. I didn't even know if said API existed. I assumed it did, and I had never, really had to build out the front end of a web application before. And so when I set out to do that, when I kind of created that scope, I had in my mind of like what I wanted it to be and what I wanted it to look like. And I knew that, there were certain steps that I would have to take to get there. And I knew that it was all within the realm of possibility. And so to start that, right, the thing that I started with was, of course, going and talking to somebody, yourself, who'd done something like that before. Because I find that, yes, you can spend time on the internet and, try and figure stuff out yourself. But, when you're talking about time, being a finite commodity, then going and talking to experts, talking to people who have experience with the technologies that you're looking to implement is usually, for me, I found probably one of the first and best steps that you can take. So kind of the short answer to the question is, I went to somebody who had done it before, got the broad brush guidelines, and only then did I start digging into, the documentation on the website and
Yeah, I think you just provided an excellent solution to the question that how to get out of tutorial hell. So there's something called tutorial hell that you keep working on tutorials after tutorials, but you can't get some product done. So as you said, talk to someone with experience is the first step to see a big picture and probably get out the tutorial hell. Yeah.
Yeah.
Okay.
Yeah.
Go ahead. If you
can say one comment about tutorial hell, because I've been there, and I know why people get stuck there. It's because tutorials are appealing because they're relatively easy, right? They're all set up for you. All you got to do is just kind of follow along. But to actually go and do a project on the skill set that you've just learned, that's hard because it requires you to go out and get data that's going to be messy. You're going to have to clean it, and then you're going to have, it's not a clean, nice tutorial. So there's a whole lot of extra work involved. And so there's just kind of a natural human hesitancy to want to go down there.
Yeah, I agree. I totally agree. Yeah. All right. So let's get to some technological knowledge and background. So the first question is involve computer hardware. So can you tell me the difference between a CPU and a GPU, and why GPU is preferred in deep learning?
Yeah, so I guess at a broad level, your CPU is designed, well, so they're both, processing units, but they're designed differently, and they have different applications. So a CPU has its processing unit is going to be faster and better than that of the GPU. And just, I don't know exactly how to describe how they're architected, but what I do know is that a CPU is designed to process a task quickly, as quickly as possible, and therefore is very good for like sequential tasks. So something that has to be done in a sequential order. That's what you'd use a CPU for. Whereas graphical processing units are architected in such a way that allow for, parallelization of a task, or breaking up a task into parallel streams. So like a CPU, I have a Mac, it has 8 cores, whereas a GPU, take your modern NVIDIA GPU, is going to have thousands of cores. And so the reason why they work so well with deep learning is because deep learning, you're doing, you know, hundreds of thousands of matrix multiplications and, you know, gradient computations. And so that is what's called embarrassingly parallel. You can parallelize all of that. And so GPUs work great for that. But if you had a task that you couldn't parallelize like that and required it to be done in a sequential step, a CPU would actually be better because it's going to be faster than a GPU would be.
I see. Good. Good. Yeah, I think I'm satisfied with your answer. The next question is about deep learning techniques involving, for example, dropout and batch normalization. So let's try to define batch. So what's the definition of a batch? And what's the advantage of using mini batch?
So batch in deep learning just refers to your training set. And so if you were to, so as you run that batch through the network, through your deep learning network, one epoch, you know, one pass through that training set, it would be called an epoch. And if you're using batch, gradient descent in this example, you would do the entire, you'd calculate your, you would run your calculations on that entire training set. And you would take one step down the gradient after processing the entire batch.
So what's the advantage and disadvantage of doing so?
So the advantage of doing that is that it's going to be a good step, right? Because you've seen the network has seen every single example. So that step is going to be you can almost guarantee it's going to be a step in the right direction. The disadvantage to that is that it's going to be, especially if you have a really large data set, it's going to be really slow to get to the optimal, you know, the global optimum in that case. So, so on the extreme end of that, you could do stochastic gradient descent, which does, you know, the same thing, but you're using one training example per epoch, right? And that's quick because you're just doing it on one training example per time. The disadvantage, of course, is it's going to be very erratic. You're going to go up and down. It's going to, you know, go everywhere, and it's not going to actually ultimately converge. It'll be close, but it will never, you know, it'll circle around the global minimum. The obviously the best method would be to use mini batch gradient descent, which is, you know, some number of training examples between one and the entire set, and that has the benefit of the model seeing a chunk. So it's going to be a randomized, you know, selection of the data set, and it's going to see a chunk of that, and it's going to calculate the gradient based off of that chunk of data. And so what ends up happening is it's going to converge quicker because you're taking less steps to get to the global minimum. So what I mean by that is one epoch, so one pass through that entire training, one pass through all of the training examples with mini batch is going to be, I don't know, depending on what you set your mini batch size to be. Let's say it's going to be, you know, you have, I don't know, 1,000 batches that you're going to see. That 1,000 is going to get you quicker or closer to the global minimum than if you did it the entire training set one thing at a time. And so mini batch, you know, in terms of like the size of those batches, is it's going to be a hyperparameter for the model. And from what, you know, from what I've seen, that it can actually be one of the most important hyperparameters that you set.
Yeah, that's right. So in your practice, what's the initial starting point for mini batch size? Like what number would you choose to start with? Like 8, 4, 100?
So typically 32 or 64 is what I've seen. And I know that for computational reasons, you want to use a power of 2.
Yeah.
But typically I've seen 32 and 64 is the starting point.
Yeah, I agree. Yeah, 32 is usually the first guess. Okay, that's good. So next question is also about deep learning. Since I know you are looking for deep learning jobs, the question is, what is a dropout layer and why it is important?
So A dropout layer, well, the reason why it's important is because it regularizes the model, right? It prevents it from overfitting, which is what deep neural networks do really well. They're really good. They're really good at overfitting. And so a dropout layer is a layer that you'd put in after one of the hidden layers. And it's basically a matrix which turns off randomly the some of the nodes. So what I mean by that is, in practice, you'd set like your dropout layer to a keep probability, and with a
Mm-hmm.
probability, let's say 80%, it'll keep 80% of the previous layer's nodes, right? And the others it'll turn off with a 0. So it'll multiply the next layer by 0 and turning off 20%. And so on and so forth. And that too is, the keep probability is another hyperparameter that you have to kind of tune to figure out what's the best, which one's going to be the best that's going to, regularize that model and thereby improve your accuracy on the validation set. Of course, when you do that, you're going to suffer it's not going to, because you're not getting all the information through, you're going to suffer loss in accuracy on your training set. But that's fine if because the ultimate goal is for it to generalize anyway.
Yeah, I agree. Like if your neural network is robust, the information shouldn't flow through like a one channel. If you drop that specific node, that specific connection, your neural network should still function properly. That's the ideal case. Yeah, good. Next question. So what is a phenomena called gradient explosion or gradient diminishing, and how are they solved?
So yeah, the exploding gradient problem is, so matrix multiplication, right? You're passing through, you're passing information through the network, and you're having all these numbers getting multiplied over and over and over again, and then you have to do the backwards way through backpropagation. So if you have a really small number to start with, and then that gets multiplied by a really small number, and then that gets multiplied by a really small number, that's going to be called that's going to eventually, that's the vanishing gradient problem, because you have all these numbers that are less than 1 being multiplied together, and that's going to get a number really close to 0. And the problem with that is when you go through and you go backwards and you're calculating your gradients, you're going to end up with a almost like a plateau, right? So it's not going to, your updates are going to be really small, and you're not going to really move anywhere. So not me, but some really amazing deep learning researchers came up with ways to solve this. And one of the ones that I know about is making sure that your initialization, your random weight initialization, is set really well. The algorithm for that, I can't remember what it's called. I think it's the HE or He algorithm, and then the Xavier algorithm, which is where you take a random number and then you multiply it by the square root of like 2 over the number of layers in the initial hidden layer, or the initial input layer, and that kind of you use to set all of your initial weights. And so that actually has a phenomenally or a remarkably good effect on ensuring that the exploding or the vanishing gradient problem doesn't persist. The opposite of that is what you first asked about, which was the exploding gradient, which is the exact opposite of the vanishing, which is where you multiply a number greater than 1 multiple times. It's going to get into too big of a number, and it's going to be unwieldy, and the model can't use it to calculate gradients effectively. That I'm not exactly sure how you prevent, other than ensuring that you have, oh, you know what? I do recall that there's a way to do that, is random weight initialization, making sure that your input, all of your input is normalized, right? So subtracting the mean and dividing by the standard deviation for
Normalize is a correct keyword.
Yeah. but then also using batch normalization. So after the input has passed through one of the hidden layers, but before it gets pushed into the activation function, is making sure that all that output is also normalized through a batch normalization error or batch normalization function. So that is one way that they found to, smooth out the gradients so that they're not exploding or vanishing.
Yeah, a quick follow-up. In terms of avoiding explosion or diminishing gradient, which activation function would you choose? Sigmoid or ReLU?
So ReLU,
Mm-hmm.
sigmoid went out of style, I guess, a while back in terms of not on the very last end, or because if you're doing binary classification, sigmoid works just fine. But in the hidden layers, you wouldn't use sigmoid because it tends to flatten out the gradients to zero when the numbers are really small.
Good. Okay, so next question. Suppose I'm someone who don't know how neural network works. How would you explain the idea of momentum to me?
That's a great question. It assumes that I know how momentum works. I think, yeah, so momentum is
conceptually, not necessarily numerically or mathematically, just conceptually, like you can get a real world example, something like that.
Okay.
So I don't know much mathematics and I don't know what a neural network is, but you can explain the idea of momentum successfully, I believe. Yeah.
Okay, I will try. I'll do my best.
Mm-hmm.
So what I'd say is, hey, if you don't know how neural networks work, then I'd say one of the ways that we try and get a neural network to find the target is through something called a cost function. And we try to minimize that cost function. And we do it through all these numeric computations. But one way of thinking about that is imagining a bowl, right? So imagine a bowl, and that bowl is covered in carpet, right? So maybe that's kind of a weird thing to think about, but bowl is covered in carpet.
Yeah.
And the target is right in the middle of that bowl. And you want to take in order to find out where that is, you have to take, some object like a bowling ball and roll it down the bowl. And wherever that ball lands in the bowl, that's your target, right? Because it's found the best place for it to rest.
Yeah.
That's the best I can think of. And if you don't want to think about it mathematically. And so you roll that ball, but because it's carpet, it wouldn't go as fast as if the bowl was made of ice or metal or something. It's going to go slower.
So that's perfect example. Yeah.
Okay. So momentum allows you to roll the bowling ball down that carpeted area, but allows you to add the momentum from, actually, you know what? I should have used like a snowball or something. That would have been a better example, because as a snowball gains momentum as it gains mass, going downhill, and that snowball is going to move faster as it goes, as it starts picking up mass, as opposed to when it's at the very top and it's really small. So that's how momentum works, because momentum is taking into account the gradients previously and kind of adding it into the ones moving forward.
Yeah, that makes sense. It's like what happened in the previous iterations will have an influence in your future iteration, basically. Yeah, that's good. Good. That's all the deep learning related questions I have. So let's do a quick Python coding question. So can you share your screen and open your favorite editor, Jupyter Notebook, VS Code, whichever you like, and I will tell you the question. Yeah.
Sure. I think I have a Jupyter Notebook open right now. Let me launch a new one. Okay, and then share my screen. Okay, can you see it?
Yes, yes, I can see it. Can you make it a little bit larger? Like, yeah.
Yep.
You can also close the sidebar by clicking that file icon, the folder icon. Yes, yeah, it's good,
Nice.
good. So let's say we have a function, a mathematical function, which has a root somewhere, like I don't know, somewhere. So, but I tell you, the root is between 0 and 2, for example. Can you use the bisection algorithm to find out the value of the root? Let's say the function is fx equal to x minus 1. So it's just for demonstration purpose, it's just a linear function, pretty simple. So fx equal to x equal to 1, x minus 1, then let's find the root of this function, which obviously is 1, but I need you to do it use the bisection algorithm.
Okay.
Is it clear?
Yes. What was the function again?
X minus 1. Yeah.
Oops. So
So
just like
you already know it has a root at 1. Yeah. Okay.
okay. Um, so f of x so yeah, f of x equals x minus 1.
Yeah.
And so that's going to be that's going to be a linear, or that's going to be a line through.
Yeah.
Okay.
So now I tell you, let's start from the interval 0 to 2. And I tell you there is a root in between, and use bisection to find it out. So you not necessarily start with exactly 0 to 2, because if you start with 0 and 2, the first guess you get the correct result. Yeah, let's say from 0 to 3. Yeah, from 0 to 3, then you find the true root, which is 1.
All right, so let me think about this for a second.
Yeah.
All right, so we are going to solve this through bisection, and the parameters are going to be, A and B. So the left side and the right side.
Yeah.
And then
you can also pass the function itself as the argument if you want. So in Python, the input of function can be a function itself.
True.
Yeah. But that's just a suggestion. If you're not comfortable with that, fine. Yeah.
Okay. I'm going to leave that for here for now. And okay. So bisection is, we're going to look at that interval between A and B.
Yeah.
And have it, right?
Yeah.
That's bisecting it. And we're going to say that midway point between A and C, if you multiply those two and they're greater than 0, then that means
they have the same sign.
They have the same sign, right? Either negative or positive. So that means it hasn't crossed the 0 axis. So
exactly.
So you're going to make that C the new A, and then
or B. Yeah.
Or B, right?
Yeah.
Well, in this case, it would be A because it hasn't crossed the line yet. So you're going to make that the A, and then you have your B stays the same, and you're going to have that.
Yeah.
And you're going to go on and so forth and continue to do that until you've reached some tolerance level. So actually tolerance should probably be
parameter. Good. Yeah.
Okay.
You can set the tolerance a default, so you don't need to worry about that.
Okay. So I think I'm going to want to do a while loop, and let's see, B minus A.
So you can do it in two ways. You can use recursion, or you can use while loop. It's up to you. Yeah.
Okay, and what was it? What did you say we're gonna? What was our original starting parameter? You said 3 and 0.
Yes, 0 and 3, one
Okay.
on left, one on right. Yeah.
0 plus 3 divided by 2 is going to be 1.5. So we'd want to look between 0 and 1.5. Yes. Okay. I do need a function here. You're right. Actually, I'll just call it f. Okay. So while c is greater than or equal to tall, we're going to multiply.
Is it C or FC? Because the property of a root is not itself being 0, but the value of that C, FC, is close to 0 enough, right?
Yeah, you're absolutely right.
Yeah. And is it also possible that C can be negative value? Like should you consider the absolute value as well? Because the tolerance is a positive number, right? But FC itself can be slightly above 0 or slightly below 0, right?
Mm-hmm.
Yeah.
So let me think about this. So function C. So FA plus FB, oops, divided by 2. Got to put this into that.
So C now is the average of two values, like so FA and FB. So here's the case. Since we are using a linear function as example, so now what you get is essentially FC. So C now, like this value C is essentially FC, but this is the linear function. So this relationship may not hold true for other functions. Let's say fx is a quadratic function. So then this relationship may not hold true. So I think your original thought is correct. Like C is the average of A and B, you find the middle point. But like the middle point may not be the, may not be the, where the root is. So you calculate FA and FC, compare whether FA and FC have the same sign. And then you compare FC and FB have the same sign or not.
So hold on, A plus B, oops.
This is correct. Yeah. What is not correct is the condition of the while loop.
Oh, right down here.
Yeah. So I will give you a hint so you can think about that. Maybe it should be, well, the absolute value of FC is greater than the tolerance. So you can draw the function, draw the function I can draw it for you on Wolfram Alpha. Then you can take a look. It can be very quick.
I'll do it real quick. So
Yeah.
One space. Let's do 2 through 200 values. Fx.
Yeah.
Okay.
Yes, that's correct. Maybe you can. You need to
let me shrink that figure size real quick.
Yeah.
Oops. What do we usually do? Like 8 by 8?
Yeah, that's okay. Because we enlarged it, so it's becoming too large. One more, yeah, red parenthesis. I think it's a figure size, not size. Yeah, good, good.
Make it a little smaller, maybe.
Yeah.
6, 6. Here we go.
Yeah.
A little too big. I think it's because.
Yeah, because we enlarge this, yeah.
Yeah. Okay. So there's our function. Yeah, so in between the interval 3 and 0.
Yeah. So you can set x from 0 to 3, actually. That would be easier. Not from -2 to 2, but 0 to 3. The x, the length space, linear space, from 0 to 3. Yeah. Okay. Now you can see 0 now is A, 3 now is B. So the C is 1.5, right?
Right.
So you calculate the sign between the product of FA and FC, which is negative. And then calculate the FC times FB, which is F1.5 times F3, which is positive. So now your C is your new B, then you continue the loop.
Yeah.
Yeah.
Okay.
So what's the condition of the while? Yeah.
So while absolute value of f of C
yeah.
is greater than the tolerance, then you're going to multiply.
Yeah. You can write down comments to help you think. Yeah.
Okay. So your product is going to be f of
A times
f of
C.
C.
So this is your, I would say, essentially your left product. So it's not the right side product, but it's okay. So should you compare it with the tolerance or 0?
Well,
because tolerance is
0, probably 0.
Yeah.
Because of the signs. Okay, so if the product is greater than, because if they're both negative, then it's going to be positive. If they're both positive, it's going to be positive.
Yeah, so not this side.
Yeah. Then your new, what happens? Then B
becomes
equals C.
C, yeah. How about C?
And then, so you've got A and C for your first interval. Yeah, 0 and 3 is your first. No, that's a bisection. So AC. Then your
So basically 1.5, your C becomes your new B, right?
Mm-hmm.
But
But your A is going to stay, your A is going to stay your A. You don't, because you're not going to change that.
so Chris, let's do this. Let's not use AB, but use low, high, and rename C to middle. So this simplifies our thinking. Let's just do this quickly so we don't need to map A, B, C to the geometric values.
Okay.
Yeah, let's rename A to low, B to high, and C to middle so we can think about that. Gotcha. Easier, yeah.
Yeah. Trying to figure out the quickest way to do this, maybe.
Yeah, just change the function signature. Yeah, low. Yeah.
High. Okay. And so this is going to become middle equals high plus low divided by 2.
Yeah.
And while the absolute value of
middle, which means we're not there, then is F low. A is low, I think. Oh, you said A is low. Yes, A is low. C is middle, which means this is the left side, right?
Yep. It's on the left side.
If product is greater than 0 on the left side, it means it's not in the left side.
It's not.
It's not.
Yeah. So your new, so your C then becomes your
A.
Your A.
Yeah. So
and your B
remains just
B.
Yeah, the high remains the high. Yeah. So let's fix this.
So if that's the case,
yeah,
then middle
become all low become middle.
Yeah.
Yeah. So basically, your current middle becomes your next round low. So that's right. Yeah. But how about the middle? You have to update the middle as well because in the condition loop, you need the new middle.
That's right. Low equals that middle, and then your middle will be
essentially the first line in your function.
Yeah. Will be middle plus high by 2.
It should be low plus high.
Oh yeah, because we just changed.
Just changed it. Yeah, you have a new low. Yeah, right. Good. How about another case? If the product is smaller than 0, it means it is in the left side.
So now if it's less than that, then that means that you have crossed the it has crossed the 0, or crossed the x-axis.
Yeah.
And so it's in that interval.
Yeah. So you need to update the high. Your next round high is the middle. Right?
Yeah.
Yeah.
So then so high plus low divided by 2, your middle.
Essentially symmetric. Yeah, symmetric to another branch.
So if it's less than that, then your high is going to equal your middle.
Yeah. And now you have a new middle, just as another branch.
I think it's going to be the same thing. It's going to be
it's the same thing. Yeah. Yeah. I think I would say that's it. Then you just exit the while loop, return the middle, right? Because every time you need to calculate the F middle again. So that's it.
And yeah, you've reached your tolerance. So then And then, yeah, then you found your root.
Yeah. The root is the middle. Yeah. Okay. I'll give it a try.
Okay.
So you can shrink your browser a little bit smaller so we can see. Yeah.
That better?
Good, good. Yeah.
Okay. So we know that the root is going to be 1.
Yeah.
So let's see what this thing finds.
Yeah.
Section. Oh, my
0.
my Galvanize instructor Kayla Thomason would kill me. Kayla Thomas would kill me because I didn't write a doc string here. So
okay, yeah.
0, 3, and our
F.
tolerance will be
in the F as well. F. Because you said F as input.
That's right.
Yeah. F. Yeah.
F.
Yeah, that's it.
For F, I need to pass in a.
So you because you defined the function as F as well in the first cell, so it's fine. So okay. F is already defined. Yeah.
Wow, look at that.
Yeah, that's it. That's very close to 1, and it's up to the precision you define. Yeah.
Let's get a better one. Yeah, it's even better.
Good, good, good. It's very nice. Yeah. Yeah. Refresh your Python memory. Yeah.
Yeah, no, that was good. That was a good call going with the low, middle, high instead of the ABC, because that was.
Yeah. Yeah, you don't need to think about the meaning of those ABC. Now the name size for itself.
Yeah.
Yeah. Okay. Good. Good. So that's about the end of the interview. So I think you did a very good job. Finished a lot of questions, both conceptual questions as well as coding questions. A little bit of struggle, but then you'll figure out the way pretty quickly. Okay. So do you have questions for me regarding today's questions or comments?
So I actually do have one. You'd asked about the exploding gradient problem, and I had suggested, making sure you get your weight initialization correct, and then batch normalization.
Yeah.
Is that the answer that you were looking for?
Yes. Yes. So you can approach this problem from several directions, like a good initialization. Randomization definitely is one. Another one is you said batch normalization. Then third one is to pick the correct activation function, because sigmoid is, I would say, comparing to the ReLU, is easier to to cause explosion or diminishing, gradients. Yeah, I think that's the correct answer. Yeah.
Good. Thank you.
Good. Good. All right. So we will stop here and let's stop recording.